To the lesson 12 of industrial instrumentation. In this lesson, we will basically study flow meters. As you know, the three basic process parameters are pressure, temperature and flow. However, if you look at the number of sensors available or the varieties of the particular process parameters like pressure, temperature is much less compared to the flow. The reason is that the flow you will find, not only the type of liquid flowing through the pipe, or it also basically depends on the what type of liquid is flowing. So, depending on that, there are various types of flow meters available and used in the process industry. There are sometimes volumetric flow, there are sometimes mass flow, there is sometimes positive displacement flow, there is open channel measurement, there is a closed channel measurements. So, depending on all these circumstances, the number of the flow meters are the highest among all the process parameters if you look at. Now, in this lesson basically we will discuss the contents of this lesson rather is the flow meters. We will just give the name of the different flow meters, then we will discuss in details the differential pressure flow meter. Flow transmitter also we will discuss in some brief, and also we will show a separate video on the flow transmitter. And now commonly used flow meters are like this. We have differential pressure flow meters, then we have variable area meters. Now, in the differential pressure flow meters, we will find we have basically or most commonly used the orifice meter and venturi meter, then we have elbow meter, then we have pitot tube. These are all basically depends on the differential pressure. We have variable area meters. One of the variable area meters is the rotameter, which is very commonly used in the process to get a rough estimate of the flow measurements. Then we have positive displacement meters, and positive displacement meters is a meter by which it's you can get the not exactly the flow velocity, but the quantity of liquid flowing in a particular situations. One of the common example of the positive displacement meters in the gas stations or petrol pump. If you go to the petrol pump and take some amount of petrol or diesel, whatever it may be, you will find that actually I am not interested in the flow rate, I am interested in the total quantity of the liquid. So, that type of situations we need positive displacement meter. Then we have a turbine flow meters, which is directly electrical output you will get from the turbine flow meters. We have electromagnetic flow meters. It also has some relative advantages and disadvantages. You will find the electromagnetic flow meters is very good because there is no obstructions and all those things we will discuss later on. We have voltage shading flow meters. Then we have ultrasonic flow meters. Well, using the ultrasonic sounds we are measuring the flow, and it is basically non-invasive, and it is like a electromagnetic flow meter. It has also it does not create any pressure loss. But if you look at the other like differential pressure meters, even though it is used extensively in the process, you will find there is a permanent pressure loss in the pipe. We have cross correlation flow meters also. These are all glimpses of the flow meters available in common or commonly used in the anywhere. Like the municipality water supply or the chemical plant or steel plant, everywhere you will find this type of flow meters. We have also laser Doppler flow meters. Now, if I look at the closed channel meters, you will find that I will just giving the glimpse. I have not come exactly to the details of the exactly the text of this our particular this lesson. Now, closed channel meters, if that means the closed pipe, I am interested to measure the flow. In that type of situations, we have obviously we will mostly use the differential flow meters, and differential pressure flow meters we have two Venturi meters and orifice meters. This we are going to discuss in very much details, right. We have variable area flow meters as I discussed. This is also closed channel meters, and it is a rotameter one is one of the good example of the closed channel meters. I mean variable area flow meters, which is used in the closed channel. Then in open channel meters, in some situations we need to measure the open channel. Like one of the good example is the irrigation purposes. If I want to know the flow of the fluid, okay, velocity of the fluid, by which we can calculate the total quantity of the liquid is used for the irrigation. In that type of situations, it is open channel. So in that open channel meters, we have basically two types. One, it is the weirs. We have a V-notch weirs and rectangular weirs, and we have also pitot tube. Now, pitot tube is basically can be used basically used for the gases and gases, clean gases rather, and it can be used for both open channel and closed channel. That is the advantage of the pitot tube. But however, in this particular lesson, we will discuss basically these differential pressure flow meters. Others will be like variable area meters, VS pitot tube will be discussed in the subsequent lessons. Now, total quantity of liquid is obviously what is that? That is the time integral of flow rate. If I measure the time and multiply by the flow rate, if the flow rate is uniform or average, so if you multiply by time, I will get the total quantity of liquid flowing in through a particular cross sections. Now, at the end of this lesson, the viewer will know the principle of operation of a differential pressure flow meter, orifice meter, Venturi meter, discharge coefficient of a Venturi meter or orifice meter, then pressure tappings. There are various pressure tappings available that will be discussed. Pipe bending near the differential pressure flow meters, because whenever you are using any differential pressure flow meters, there is a restrictions of the pipe bendings both upstream and downstream, that you must look at, right. Then pressure recovery, because you see the differential pressure flow meters, there is a permanent pressure loss, and permanent pressure loss means pumping, extra pumping cost. So that you have to take care, and this is very crucial in the case of any water supply and all this thing, because pumping needs a lot of money involved, so that the whatever you are supplying the water or other things, the cost will be increased. Now, what is the need of flow meters in a process? First of all, we know that flow meters is necessary for the, so suppose in the water supplies, flow meter is necessary because I know how much quantity of liquid or water I am supplying to the particular town or city, that is one thing. But what is the need actually in the process? Measurement of the volumetric flow rate and mass flow rate are necessary for the purpose of determining the proportions of materials introduced to a process and the amount of materials produced in the process, right. Measurement of volume flow rate, you look at. Now, differential pressure flow meters comes under these. They are most widely used flow meters for liquids and gases. A restriction or constriction is placed in the pipe, and the differential pressure developed across the restriction is measured. As simple as that. It is very simple principles, just applying Bernoulli's equations you can find the flow rate, and the differential pressure output is calibrated in terms of volume flow rate. So, that differential pressure is calibrated in terms of volume flow rate, then we are converting into the current and all those things that will be taken care later on. Now, you see this is a typical differential pressure flow meters, the schematic of the differential pressure flow meters we can see here. You see, if I look at, I do not know which, fine, this I can take. You see here, this is a pipe, liquid is flowing through these directions. Liquid is flowing through this direction, it is coming out this direction, clear. And you see there is a restriction, this is our restriction, okay, in the form of orifice. It is basically a circular plate, please note, okay, there is a hole in the, a concentric hole in the middle, a circular plate. So, liquid is flowing through this plate, so liquid is coming and it is flowing through like this one, okay, clear. So, it will not be exactly like this one. So, let me go back again. So, it will look like this one. So, the liquid will flow and there is a minimum pressure area after that. So, it will go then after that liquid will flow like this one. Clear? Now, the area of cross section in the upstreams we are taking A1, area cross sections of the restrictions or the constrictions is A2. P1 is we are measuring the upstream pressure tap, we are calling it upstream pressure tap. P2 is the downstream pressure tap, P2 is the downstream pressure tap, P1 is the upstream pressure tap, and Z1 and Z2 is a height of this central point of this area of cross section of the pipe as well as of the at the point of measurements of upstream pressures as well as the orifice plate, right. So, we are making it Z1 and Z2. Let us go back. Now, if I apply the Bernoulli's equation across these two sections, will upstream and downstream, easily I can write P1 by rho 1 plus V1 square by 2 plus Z1 into Z equal to P2 by rho 2 plus V2 square by 2 plus Z2 G. So, unit you can say all the dimensions are equal, it is all are it is a meter per second square in units of the individuals. So, it is we have taken it per unit mass. So, we can write this Bernoulli's equation like this, right. Total height of the liquid at any point is same, that is the basic principle. P is the pressure in Newton per meter square, V is the average velocity in meter per second, V1 is the upstream velocity and V2 is the velocity at the restrictions or the minimum area, and rho is the fluid density which is kg and meter cube, everything in SI, no problem. A is a cross sectional area, it is in meter square, and Z is the elevation above the bottom level. Okay. So, you can take any bottom levels, obviously this is not very important if the pipe is horizontal, and that is in meter. So, the following assumptions have been made in calculating the volume flow. So, you have to make some simple assumption to calculate the volume flow rate. These are: the flow is frictionless, it means there is no loss of energy due to friction either in the fluid itself or between the fluid and the pipe walls. There is no heat losses or gains due to heat transfer between the fluids and its surroundings. There is conservation of total energy, pressure, kinetic and potential. We have written the Bernoulli's equation from that only, right. So, it is nothing new. So, there is conservation of total energy, pressure plus kinetic plus potential at any point of the liquid. The fluid is incompressible. So, it is rho 1 equal to rho 2 equal to rho, right. So, that the density is same everywhere, and the pipe is horizontal, that means Z1 equal to Z2. So, it means that the equation 1 reduces to V2 square minus V1 square upon 2 equal to P1 minus P2 by rho. Now, conservation of the volume flow rate, if it is there, so we can write Q1 equal to Q2 equal to Q, that means Q1 is the upstream flow volumetric flow rate, Q2 is the downstream downstream volumetric flow rate. Also, we know Q1 equal to A1 into V1, A1 is the area of cross sections of the pipe and V1 is the pipe and the fluid liquid flow diameter flow velocity. Q2 is the downstream flow velocity, obviously Q1 will be equal to Q2, this will be equal to the area of cross section of the orifice multiplied by the velocity of the liquid at the orifice. Obviously, if the P1 is greater than P2, that will come in the next slides. Let us go to the next slide. So, since A2 is less than A1, it follows that V2 will be greater than V1 and P2 will be less than P1, right. Since A2 less than A1, it follows that the V2 will be, that is obvious from the last equation, V2 will be greater than V1, and that means the flow velocity at the restriction or at the minimum area of cross section is high, okay, compared to the actual flow velocity, right. We are not interested in that, we are exactly interested in the volumetric flow rate, that is same both in the upstream and downstream. Therefore, the theoretical value of the volume flow rate in a differential pressure flow meters both in the case of venturi and orifice is that Q theoretical we are writing is A2 upon under the square root 1 minus A2 upon A1 square under the square root 2 P1 minus P2 by rho. This is equation number 2. The theoretical value of the volume flow rate always differs from the actual flow rate due to two main reasons. There is some restriction, why I am calling it theoretical, we will find that they have to multiply by some discharge coefficients to get the actual flow rate, okay, actual volumetric flow rate. The frictionless flow is never occurred in pipe. It is true for turbulent flows in a smooth pipe where friction losses are small. The laminar and turbulence flows are characterized by the Renault number, and Renault number is given as Re equal to V dP by eta. Okay, this will give you the Renault number, where d is the pipe diameter, eta is the viscosity of the fluid flowing in the pipe, V is the velocity of the fluid in the pipe, and P is the differential pressure across the section of the pipe, right. Number 2 is A1 and A2 are the cross sectional areas of the pipe and the restriction respectively. The cross sectional area of the pipe is pi d square by 4 obviously, and the cross sectional area of the meter, orifice meter or venturi meter, it is pi d square by 4, where d and capital D and small d are the respective diameters. That means pipe diameter, internal pipe diameters, and this is the diameters of the orifice or the throat diameter of the venturi. If the fluid fills the pipe, then A1 equal to pi d square by 4. However, the area of the minimum cross sectional area will be not exactly at the restrictions. So, it will be 0.99 pi d square by 4 for a venturi meter, because venturi is not a sudden restrictions. However, the orifice plate is a sudden restriction which causes the fluid cross sectional area to have minimum value of 0.6 pi d square by 4 at the vena contracta. That means, it is a little far off from the orifice plate, where you will get the minimum area of the cross section of the fluid, right. Therefore, the theoretical expression of volume flow rate is corrected as C. We are introducing a new factor C under the square root 1 minus beta to the power 4 multiplied by A2 under the square root 2 P1 minus P2 by rho, where C is the discharge coefficient and beta is the flow meter pipe diameter ratio small d by capital D, and A2 is the flow meter cross sectional area, this is equal to pi d square by 4. Values of the discharge coefficient depends on type of flow meter, that is orifice or venturi, Renault number Re, diameter ratio beta. So, therefore, for a given flow rate flow meter, I can write C equal to is a function, C is a function of Re, Renault number and beta. Values of C are found experimentally for several types of flow meters over a wide range of fluid velocities, right, because flow meter C velocity should be known to you. For a given fluid and known volumetric rate of fluid flow, C can be found from the equation 3. If the fluid volumetric rate of the fluid is known, so obviously I can, and if the density of the fluid is known, so obviously I can find the value of C. Now, general features of the differential pressure flow meter. So, what are the general features? Let us look at. These are most important, that is the reason it is used widely in the industry for last several decades. Number 1, it has no moving parts. Okay, you look at, there is no moving parts. So, it is robust, reliable and easy to maintain and widely established. It is established over the years, it is documented, data are available. So, all these things, all these supports we are getting from the past users. So, that is the reason it is used widely in the industry. Number 2, there is always a permanent pressure loss and extra pumping energy. This is not a good feature, this is a bad features obviously. So, there is always a permanent pressure loss and the extra pumping energy is necessary to overcome it. So, whenever there is a permanent pressure loss, I have to need some extra pumping energy. So, obviously, this pumping energy needed in the case of orifice meter is more than that of the venturi, because venturi the permanent pressure loss is much less. Now, let us look at, you see it very carefully. So, you see here that if I look at the from this one, so you see this is our pipe, this is the distance from the orifice, we are taking orifice or venturi throat. Here you see at the differential pressure measured, here there is a sudden fall of the differential pressure near the orifice. Okay. After that, we are this pressure loss is, it is pressure. So, this is a pressure recovery. There is a sudden pressure loss, this is good for measurement. So, wider the pressure loss, if it is temporary, that is good for measurement, because we are getting, we can, our sensitivity of our instrument will be higher, because if you see here the pressure loss should be always will be higher and higher. Here pressure drop or differential pressure should be higher and higher, because in that case what is our input? Input is the flow and output is the differential pressure. So, differential pressure by flow, if it is higher and higher, obviously that is better for us, because static sensitivity will be increased in this case, right. But you see this should not be permanent. That is the problem with the orifice meter. So, you see there is a permanent pressure loss that will never recover. So, I need extra pumping energy to overcome this pressure loss, right. So, this is most important, right. You see this is a permanent pressure loss, say there is a temporary pressure loss we are measuring at this point preferably, then there is a permanent pressure loss, right. Now, both Venturi and orifice meter is non-linear, that is most important. If you see volumetric flow rate is proportional to the square root of the pressure differential, right. So, this limits the useful range of a meter in between 25 and 100% full scale output reading. At lower flows, the differential pressure measurements is below 6% of full scale output reading and is not accurate enough for the measurement. Now, you see there, so useful range here you see it is a nonlinear curve. So, because you can see that the flow velocity or the quantitative flow volumetric flow rate is proportional to the square root of the differential pressure. So, obviously, it is nonlinear. You can see here that if the flow velocity is less than 25% of the full scale output rating, if the full scale output reading is here 25% of the full scale output reading. So, the whatever the measurements we are doing, that is much erroneous, right. So, it is not very good for the low flow measurements, it is good for the higher flow measurements. That means, the error will be less in this case, right. This error you can see here, excuse me. So, error you see here, error here is quite low at the low flow velocity, quite low at the high flow velocity, and is very high when the flow velocity is or volumetric flow rate is low. Number 4, it can be used for turbulent flows, because turbulent flow is characterized by when Re is greater than 10 to the power 4, 10,000. A typical flow meter system consists of the differential pressure sensor, differential pressure transmitter, data acquisition systems and a PC. The transmitter gives a current output signal of 4 to 20 milliampere, and the dash consists of an amplifier, I2P converter and ADC. Right, this is our system. You see differential pressure sensing element and transmitter, data acquisition systems and PC. Please note that this differential pressure transmitter should be an assembly, or it is to be installed on the pipe itself, just outside the pipe, and it should give you 4 to 20 milliampere of current, which will go to the computers, so where the data acquisition card is there. So, through which will convert to the voltage domain and will be used for further processing after conversion to the digital domain. This 4 to 20 milliampere of current is obviously is analog current, right. Now, let us go to the instrumentation lab and look at one of the transmitters, one of the differential pressure transmitter used extensively in the industry. As you know that in the flow measurements, actually the flow is calibrated in terms of pressure. So, in all flow meters, I am talking about the variable area like orifice meter and Venturi meter. So, there is a upstream pressure tap and downstream pressure tap. We have seen in the class that we have shown on manometer sort of thing, by which I am measuring the pressure. But unfortunately, in the process, actual process, I need some instrument or some equipment which will give some signal that will be transmitted to the control room. Now, for that reasons, we need some electrical output. So, what they do in this case of this differential pressure transmitter, because there are two pressure tap, one is upstream pressure tap and another is downstream pressure tap. Now, you can see here, this is basically a capacitive type DP transmitter. Here we have an upstream pressure tap, and here you can see the downstream pressure tap. So, you can open it and you can connect the upstream pressure tap here. So, inside what we have a capacitors with the movable plates, and the inside of the two capacitors are plated with some metal. So, you will get, once the capacitor, suppose this side is high and this side is low, the capacitor's movable plate will move on this side. So, I will get a push-pull sort of variations of the capacitance, which can be calibrated and in terms of pressure, and ultimately that will be calibrated in terms of flow. Now, this is basically these capacitive sensors inside, and there is measurement circuits and signal conditioning circuits are here on this side. You can see here, if I open, there is a connection for the signals. You see here that we have positive signals because in the process the output is 4 to 20 milliampere and the supply voltage maximum is 45 volt DC supply, because in all the process, as you know, it's you cannot give the supply voltage much higher. That is also not necessary, and it will give the according to the variations. First of all, this circuit will first measure the variation of that capacitance, and that variations of the capacitance will be converted in terms of current, 4 to 20 milliampere of current. So ultimately, there's 4 to 20 milliampere of current will be calibrated in terms of flow, and the output signal we can take from this side. We can open this side and see here. Okay, here the circuitry, and we can connect here, and there is a things here, and this side you can make all the connections sort of thing for taking the both the giving the signal and taking the 4 to 20 milliampere of current. This circuitry which this actually the PCB which you can take it out for making it repairment and all that type of job. So now we will discuss particularly already we discussed the orifice and venturi, but there is some difference between the orifice and venturi meters, and also we will discuss that like Dahl tube and flow nozzle, all those things. So let me first discuss the orifice meter, which is I think if you look at the flow meters, it is most widely used flow meters in the process industry. I should say 80% of the flow meters are the orifice. If you look at the, if you compare to the number of meters, like so many meters we have discussed at the beginning, sophisticated meters, all these things, but orifice, because it is established over the years, it is one of the very widely used, cheap, easily replaceable meters, and quite reliable also. That is most important thing. Maintenance is also very easy, just replace it. It does not need calibrations. Once you have made several orifices of the from the same lathe machines, it won't take, I mean, just you do not need, if the diameter ratios are correct, is small d by capital D is same as before. If it is square edge orifice, so there is no question of making any further calibration. That is a great advantage of it. So during routine maintenance, just replace the orifice. That will simplifies. If you look at the other meters, it needs lot of, it is expensive also. So among the differential pressure flow meters, orifice is the cheapest. Let us go back to the orifice. Now it is a thin plate square edge orifice is the most widely used differential pressure flow meters. Thin plate number all, square edge orifice is the most widely used differential pressure flow meter in process industry, mainly because of its simplicity, low cost, and moreover it is well established over the years, and the data are available for its behavior. That is most important thing. Just you cannot have a new, I mean, something somewhere, I mean, in some laboratory in the world has developed some flow meters. So immediately that cannot be used. Okay, it is used over the years, and people ultimately our goal is to make our product good, is not it? So I told you several times before also, quality of steel, quality of fertilizer, quality of petrol, diesels, or quality of life. So if you are giving anywhere, I mean, some quality of our drugs which you are producing in the bioreactors. So it does not matter, I mean, what type of flow meters you are using. If the product is good, product is pure, so there is no question. So orifice meter, it is working for several years for all these reasons, and we are using it extensively in the industry. Now typically 3 types of orifice plates are available. Okay, it is basically a plate. Okay, if you look at it, looks like this, you see. So it is a plate here, and there is a hole, right. If you look at, so it will be look this square edge orifice. So it should be, if I look at, okay, so liquid is flowing through this one, like this one, clear, right. Let us go back again. So these are the 3 different types of orifice. If you look at, there is a concentric orifice, eccentric orifice, and segmental orifice. All has different applications. That is the reason we have plotted like we have given like this. So the concentric orifice is the most widely used place. The eccentric and the segmental orifices are employed to measure the flow of the fluids containing solids. In both cases, the bottom of the hole is located in a way when the bottom of the hole is at the same level inside the bottom of the pipe installation. These two orifice plates need separate calibration because the discharge coefficients differ from that of the concentric orifice. Clear? I need separate calibration for this one. Suppose I have a suspended particles, all these things. For that reasons, if suppose you have some slurries, okay, if you use a concentric orifice, all these things will be deposited at the bottom of the pipe. But if you use eccentric orifice, that will be flushed away. So, that is the reason some application for the liquid flow measurements will use concentric orifice, some will use eccentric, and in some will use a segmental orifice. The concentric orifice plate is installed in the pipe with its hole concentric to the pipe itself. It is a flat metal circular plate made of steel, stainless steel, phosphor, bronze, like that. Its thickness is only sufficient to withstand the buckling forces caused by the differential pressure exist across the plate. So far that it can withstand that differential pressures, you can use a thin plate, but it should not buckle, then the entire calibrations will go wrong. For that reasons, if you have a larger differential pressure and all these things, we have different types of flow measurements, although that also basically depends on the differential pressure flow, differential pressure measurement. Circular hole is made with 90° square and sharp edge upstream. Okay, it is a 90° that I have shown you, and sharp edge upstream. The change of sharp edge will modify the discharge coefficient of the orifice meter, and it is advisable to replace the orifice during the routine maintenance of the plant for better accuracy and of the measurement. Now, orifice pressure taps, there are various pressure taps available for the orifice. There are here in these particular lessons we will discuss 3 pressure taps, flange taps. You see there are flange taps, this orifice plate with the flange taps. Even though I have drawn like this one, you can see here, but it is actually as I told you earlier also. So, it is I will draw like this one. So, this actually okay. So, square edge like this one, right. So, but actually we have plotted like this anyway. Now, it is constructed so that the taps for the measuring differential pressure are integral part of the orifice assembly. It is the one thing is in the orifice itself, you have the pressure tappings itself. Okay, it is entire assembly available, right. The pressure taps are usually located 2.5 centimeter either side of the orifice plate. The advantage of the flange tap is that the entire orifice assembly is usually replaceable, and the pressure taps are accurately located, right. Now, we have a orifice plate with D and D by 2 taps. Here you can see that it is upstream is D and downstream is D by 2 taps. All these are some advantage and disadvantages. Then we have orifice with a vena contracta taps. I am sorry, this will be vena contracta. So, this will be contracta, vena contracta, sorry, this will be A, vena contracta taps. So, orifice, because you know the area of the minimum cross sections does not appear here, it is somewhere away from this one. Okay. And we always try to measure there at the area of the vena contracta, because the differential pressure will be if the area of cross section is low, the differential pressure will at that point will be highest. So, there is ease of measurements, our static sensitivity of the sensor will increase. So, that is the reason what the people do, because as I told you the area of the minimum cross section is not here, it is little far away. So, this is the tap where I am measuring that the pressure, downstream pressure at the area of the place of vena contracta, which is the area of the minimum cross section of the fluid flow. It is arranged in a way so that the volume, so the downstream pressure tap is located at a variable distance from the orifice, right, depending on the pipe and the orifice size. The upstream tap is at 1 pipe diameter and the downstream tap is at the vena contracta. In vena contracta tap, the pressure differential is a maximum for a given flow rate. This is important. Okay. At the vena contracta tap, pressure differential is maximum for a given flow rate. So, the pressure differential is, as I told you repeatedly, what is the advantage of the having a large pressure differential, right. Now, restrictions of the pipe fittings adjacent to orifice meter. This is another most important thing practicing engineers must follow. So, that is the restrictions of the pipe fittings adjacent to the orifice meter. There cannot be pipe fittings, pipe bendings, tees, valves, etc., very near to the orifice, both upstream and downstream. What are those? Let us look at details. The discharge coefficient are experimentally determined on straight pipes, right. Now, flow disturbances in the pipeline adjacent to the orifice alter the value of the discharge coefficient. Therefore, elbow, okay, pipe bend, T, valve are not allowed near the orifice meter. Okay. How much near, that we must know, otherwise what do you mean by near? Engineering, that is I mean this some you must quantify. I mean you cannot say just qualitatively very near or something or very far. There should be no fittings closer to the 5 pipe diameter from the orifice on the downstream. Okay. Same, no bending, no elbow, no valve, no T. There should not be any fittings closer than 20 pipe diameters upstream. Upstream is more restricted. Okay. That is we can see. If the minimum distance is not feasible, in some situation you will find it is very difficult to achieve that, because in the process you will find that the I mean it is not possible, I mean to have these pipe bendings everywhere, right. I mean you cannot avoid, because there would be some pipe bending. So, in that type of situation when the pipe bending is unavoidable, you cannot avoid the pipe bendings, I have to use some flow straighteners both upstream and downstream. Okay. What is those? What are those flow straighteners? The flow straighteners, that is clear from this. You see, if the minimum distance is not feasible, especially in the upstream, flow straighteners can be installed, and the flow straighteners are bundle of smaller tubes welded inside the pipe. It has the bundle of smaller tubes welded inside the pipe. So, it will make the flow straight. So, that the problem which occurred, that means due to the pipe bending, elbow T can be can be minimized by using the flow straighteners. Now, next type of flow meters, already we have discussed orifice meter. Next type of flow meters are the flow nozzle, dial tube, venturi meter, all are same, and orifice meter, venturi meter, flow nozzle, dial tube, venturi, these are basically same, but all depends on differential pressure measurements. We will discuss one by one flow nozzle, dial tube, then we will discuss in more details the venturi meters, because that is widely used for the large flow measurements, large quantity flow of the volumetric flow rate. This is a flow nozzle, you can see this is a shape like this one, it is a this is called flow nozzle. We have upstream pressure tap here, downstream pressure tap just above at the end of the nozzle outside the pipe, just in here we have the upstream downstream pressure tap, this is upstream pressure tap. Here you see this is our venturi tube. Venturi meter is something like this, is upstream pressure tap. This is a piezometer rings, we want to average the pressures. This is a throat tap, okay. Instead of downstream we are calling it throat tap. This is the area of the minimum cross section, okay, because there is difference of area will be A1, this is A1 area of cross section, this is capital D, this is a small d, okay. So, that ratio will give you the beta. This is the venturi meter, and this piezometer rings is to average the upstream pressure, and this is to average the downstream pressure. Now, this is the dial tube. So, we have a pressure here, pressure tap here P1 and pressure tap here P2. So, these are all basically there are some relative advantage and disadvantage of this type of things. Flow nozzle and dial tube, let us first discuss the flow nozzle and dial tube, compare, then we will discuss the venturi in details. The flow nozzle, venturi tube and dial flow tube have the same principle as the orifice. Okay. Flow nozzle, venturi tube, dial flow tube have the same principle as the orifice. Okay. No difference, same, there is a differential pressures, and we will measure the differential pressures, we will calibrate the differential pressure in terms of the volumetric flow rate. So, no difference. So, that is same, exactly same with the orifice meter, and it is a non-linear. Any differential pressure flow meters are non-linear. That means, the volumetric flow rate is a square root, proportional to the square root of the differential pressure, or if you look at the differential pressure is proportional to the square of the volume flow rate. Dial tube is a modified venturi tube, and it has a low permanent pressure loss, okay. Not low like the venturi tube, but it has a low permanent pressure loss, right. The flow nozzle are more expensive than the orifice meter, but cheaper than the venturi meter. Venturi is the most expensive, as you know. So, the flow nozzle are more expensive than the orifice but cheaper than the venturi. And it is also a variation of the venturi in which the exit section is omitted. We do not have an exit section if you look at very carefully. So, that it is similar to an orifice with well rounded upstream edge. The upstream tap is about 1 pipe diameter from the entrance to the nozzle, and the downstream tap is made on the pipe opposite to the straight portion of the nozzle. That already we have discussed, right. We have shown that thing. Flow nozzle are used for, because you know that in some situations there is a high pressures and high velocity, sometimes the orifice is not very stable, there is a question of buckling and all these things. That type of situation you have to use a flow nozzle, and we cannot spend that money everywhere, I mean to install a venturi meter instead of the orifice meter. So, in that type of situations you can use flow nozzle because it is cheaper than the venturi meter. Flow nozzles are used for high velocity steam flows, and it is dimensionally more stable at high temperature velocity than an orifice. This is the most salient features of the flow nozzles. That is the reason for high velocity, high temperatures we can use this flow nozzle instead of using the orifice meter. And the pressure tapping is also not that difficult. So, you can have upstream pressure tap at the 1 pipe diameter, downstream pressure tap just at the end of the straight portion. So, just at the end opposite to the end of the straight portion of the pipe, straight portion of the nozzle, that will be on the pipe, right. The permanent pressure loss in the flow nozzle is same as orifice. So, there is a permanent pressure loss, is quite high in the case of orifice meter. So, it is same also in the flow meter. It is the least or minimum in the case of venturi meter, right. So, whenever there is a savings of the extra pumping cost you have to consider, so you must go for venturi meter, there is no other alternative. Now, if let me discuss the venturi meters in details. Venturi meter is an expensive instrument, but offers very good accuracy. It is I should say one of the most accurate flow meters developed by the mankind. So, it is plus minus 1% accuracy. So, you can see that it is quite accurate. It has the lowest permanent pressure loss that I told several times. So, whenever there is a question of permanent pressure loss, so you can go for the this type of sensor. Now, construction of the venturi, if you look at the construction, how the venturi actually look like. It is made of cast iron or steel. Sometimes it is, if you have a larger, then I need it can be made of concrete also. Okay, large volume it can make into concrete, made of cast iron or steel. Sometimes the throat portions of the venturi, because if you look at the venturi, it looks like this, is not it? The venturi looks like this. This we are calling it throat of the venturi. So, we have a tap here, we have a tap here, you know. So, this is called throat. So, in some application, throats are made of separate metals. I mean, it is usually made of bronze because it is easily replaceable, all those things. Okay. The main systems, these both this and this will be made of cast iron or steel, right, and this is all about. The large venturi tube is usually made of concrete, because if it is very large, so it is very difficult to make made of cast iron or steel. In that case, we will use for the concrete. Sometimes the throat is made of bronze, as I told you earlier, for easy replaceability. Upstream section has an angle of 20 degree included angle. That means, if you look at, so it looks like this. If I take a white page, so it will look like this, that I have to take different colors. So, I am talking of this angle, that means, if you look at this angle is 20 degree in the case of venturi, and this angle should be 7 degree. In fact, you will find that basically there are two types of venturi. One is for the larger downstream portion, okay. Another is the smaller downstream portion. You will find that if you make this angle even lower, your pressure recovery will be also higher. So, this angle, but it takes a large space and all those things, for that is the restrictions of the venturi. But if you make this one large, you will find that your pressure recovery also will be large. In fact, the pressure recovery in the shorter venturi is less. That means, the permanent pressure loss will be more in the case of short venturi than the longer standard venturi. So, if this is large, suppose I mean if you have this type of venturi, okay, then we have that, you will find that the total length might be increased, right. Total length is increased, but the thing is that the pressure recovery will be better and the permanent pressure drop also will be less. So, this is very important. Upstream section has an angle of 20 degree and downstream section angle of 70. These are all included angle, right. The pressure taps are, this will be, I am sorry, this will be pressure taps, this will be pressure taps. Pressure taps will be are made of piezometer ring, so as to average the measurement around the periphery. Diameter ratio small d by capital E for venturi typically lies between 0.25 to and 0.50. Okay. It has almost no maintenance requirement and its working life is very, very long. Okay. So, almost absolutely no maintenance, which is necessary in the case of orifice meter, special orifice meter. Whenever there is routine maintenance, you have to check that whether the square edge section is still square edge, okay, whether the diameter is exactly remains as small d, which we have used for calibration purpose. If it is not, then you have to replace it. Usually, I mean during the routine maintenance, you must exchange this, replace those old orifice with a newer one, which is not necessary in the case of venturi, because it is a permanent, this throat made is of steel, there is no chance of increasing those throat diameter, which is there, that is in the, because if you after long use, that means if you look at that, if orifice is what I do not know. So, you see that we have the, if I take a if you take like this one, okay. So, if this edge has got a sharp, I mean instead of like this one, it is getting like this one, right, and this is getting like this one, right. So, the entire calibrations will go wrong. So, that this type of situation does not arise in the case of the venturi meter. That is the great advantage of the venturi meter. It is widely used in high flow situations such as municipal water system, where large savings of pumping costs are possible due to low permanent pressure loss across it. Okay. Usually that type of situations, I mean you say if you look at the range of these flow meters, orifice meter has a larger range than the venturi meter has a larger range than the orifice. So, there is a two great advantage of the except the cost, the main advantages of the this venturi meter is it is reliable, its range is very high, very high compared to orifice. Any other permanent pressure drop is also very low. So, keeping all this mind, so whenever you want to use, because you have to, whenever you want to use this type of meters where the accuracy is very important. So, I have to use this venturi meter, there is no other alternative, right. Now, the smooth internal shape of the venturi tube means it is unaffected by the solid particles or gaseous bubbles in flowing fluid, and in fact, it can measure the flow of liquid containing slurries. You see, this is very important, even though in the case of you will find that in futures also will some flow meters are electromagnetic flow meters, and electromagnetic flow meters are there. So, where you can use if the liquid has some suspended particles, because since there also there is no obstruction type of things. In the venturi also there is no obstructions, unlike your orifice meter, though both depends on the depends on the differential pressure meter. You will find differential pressure principle, you will find that if the liquid contains the gaseous bubbles. We have tried, you see that we have seen already discussed in the orifice meter, we have eccentric orifice, we have concentric orifice, we have a segmental orifice, but this does not suffice. In many situations you will find it does not work. If you have until unless the liquid is clean, it is very difficult to measure with the orifice meter, right. That type of situation does not arise in the case of even though I am saying that the okay you can do it with electromagnetic flow meter, but electromagnetic flow meter is a problem. That means the liquid should have some conductivity level. Say without that, suppose in the case of hydrocarbon industries, you cannot use electromagnetic flow meters because conductivity is very poor there, right. So, that type of situation does not arise in the case of Venturi meter. It does not matter whether it is a conducting liquid, not only Venturi orifice also, whether it is a conducting liquid or a non-conducting liquid, it does not matter, right. So far there is a differential pressure, I can measure it, right. And since we are not measuring with the manometers, we are using a U2 manometer, we are using some differential pressure transmitter. So, even though the liquid has some suspended particles, okay, some slurries, it does not affect our pressure measurements, right, because basically we are using a separate types of capsule type differential pressure transmitter. So, which will send some signals and give to 4 to 20 milliampere of output. Now, its range is very high, you can see its range is extremely high. It is possible to measure the water flow rate as high as 1.5 into 10 to the power 6 meter cube per hour. No other flow meter will give you this huge range. The dimensions will be quite big, that is I agree, but the thing is this type of high fluid flow rate or the volumetric flow rate will never achieve in any other flow meters. This is very important, right. And this is also, please note that this is also needed in some type of situation, because in that type of situations you will find that I need a flow meters where I need a differential pressure output, as well as I need a flow meters where I need a large quantity of the volume flow rate. In that type of situations I have to use the Venturi flow meters. So, this is very important for measurements, right. Now, another thing please note in the case of Venturi and flow orifice meters, once you install, the advantage of the Venturi meter, you will find that if you go to any process industry, you may find one or two your Venturi meters, but you will find hundreds of orifice meter because of its easy replaceability. It is very easy to replace it, just take out the plate and replace the plate with the same diameters and same thickness. So, you do not have to recalibrate your sensor, that is if the square edge orifice, if the small d is same. So, there is no question of recalibrations, and in the case of Venturi meter there is no question of that type of calibrations or anything, because its life I say that it is just if there is no wear of the surface of the internal surface, or if there is no chances of increasing the internal diameters of the pipes. So, there is no question of changing of beta. So, all these advantages make these two particular flow meters, even though you will find that there are many different types of flow meters, electromagnetic flow meters, we have vortex training flow meter, ultrasonic flow meters, Doppler flow meters, but this does not used much in any process industry. What we are using actually, you will find that this type of signals in large, this type of sensors, that means Venturi and flow in large number. Only disadvantage of this type of meter, if you look at that orifice and Venturi, everywhere you need a transmitter. Okay. I need a transmitter both in the orifice and Venturi. Is a system, not only a system, because here the output is not electrical, unlike your turbine flow meters, unlike your electromagnetic flow meters, where the output is direct electrical. Basically, it is a pneumatic output, okay, which is coming in the case of or hydraulic outputs, which is converted by capacitance change, and we are getting a 4 to 20 milliampere of current from the transmitter, which is transmitted. But if the electrical output is there, either in voltage or current, directly that can be transmitted. If in the case of voltage, we will convert to the 4 to 20 milliampere of current and transmit. These are some advantages of the non-differential type of flow meters. But whenever differential flow meters, so we are using it for a quite long, many years in the industry. So, it does not matter that what is the how much it is cumbersome. It looks very cumbersome. You have seen already in when we went to the lab and see these differential pressure transmitter. So, every orifice meter and Venturi meter must have that type of things just above the pipe. Okay. So, that should be there. So, if there are suppose 500 orifice meters, so we must have 500 transmitter also. It does not matter, you know exactly when you are getting the correct measurements. So it is ease of maintenance, is, I mean, leading all these things. If you have this type of advantages, that, I mean, pushes us, I mean, to a corner where we have no other I mean, alternative than using the orifice meters, and all the data are available over the years for the all different process industries, all different manufacturing industries. So, this helps us to make the use of this particular type of flow meters. We have discussed only this orifice and venturi. There are many other flow meters, like I told you that this is only 2 differential pressure flow meters we have discussed in this particular lesson. But please remember, we have also differential flow meters, like pitot tube is also differential pressure flow meters, elbow meter is also differential pressure flow meters in next sessions which will be discussed. So, this ends the lesson 12 of industrial instrumentation.